discussion of the micrometer screw gauge continued from our last class. It has been a bit while. So here we have the calculation that has already been shown over here because they are doing this over here. The main idea about micrometer screw gauge is that we're going to place the object face on onto here, and typically micrometer screw gauge has a thing called ratchet. Let me just show you one of these images. This is pretty much how a micrometer screw gauge looks like. This is what we call the fixed jaw. This is what we call the movable jaw. This is the jaw that is connected to a screw mechanism, which is actually a very finely threaded screw. And this is the part which we call the thimble, that can be rotated. Usually we do not rotate it for closing, we use it to opening. So which means whenever we're trying to increase the gap, we can use it to open the whole thing. And if we're trying to put an object in between the jaws and then we want to close the two jaws to take the measurement properly, we use the ratchet. The ratchet actually has a clicker mechanism. It's sort of like a soft lock mechanism that whenever the jaw is whenever the jaw cannot go further for a certain amount of pressure, it starts to do click and actually stops the movement of the jaw further in. The reason the ratchet is needed because this thing works on a screw mechanism. So whatever the object that we put in over here, we want to measure the dimension of the object. We do not want to deform the object by squeezing it hard by a screw piston mechanism, by screw mechanism. So we don't want that. So that's why the ratchet is there to stop over torquing the object or deforming the object so that doesn't happen. This is what is a manual micrometer screw gauge. Sometimes micrometer screw gauges are also available in digital. So this is a digital micrometer screw gauge. We are not going to have digital micrometer access for our lab experiences. You need to learn how the micrometer screw gauge works to begin with so that you can actually work with it. So one of the first thing that is important for us to understand is that just write this stuff. So the length measurement is done by main scale reading plus circular scale division multiplied by least count. I'm going to talk about this thing in a bit, minus plus or minus error. Main scale reading. Main scale reading is basically how much the main scale can read up to, and then whatever is left after the reading from the main scale, that is read by the circular scale or the special scale. In micrometer screw gauge, we have a circular scale, and typically the circular scale is divided into 50 divisions. For example, this is a virtual micrometer that from Professor Eduardo Stefanelli. It's a very nice simulation. So you can see over here that this is the zero mark over here. If I start to rotate this thing, I'm rotating downwards. So here you have 0, and over you have 5. This is 45. If you go down here, 40. So 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, and then 46, 47, 48, 49, and 50, which means the 0 number division and the 50 number divisions are overlapped. So you have a circular disc over here, circular scale over here, where you have exactly 50 lines, and 50 lines are giving you 50 divisions. Because the 0th line and the 50th line are perfectly overlapping, you have exactly 50 divisions on the scale. So this is from where we actually count the circular scale division mark. And in every micrometer screw gauge, we have a datum line or a reference line. This is this horizontal line over here. This is the line that we use to find out which exact mark of the micrometer screw gauge are we going to take the reading for. In many cases, not I won't say in most cases, in many cases, one mark of the micrometer screw gauge might go perfectly aligned with the datum line. For example, if we have a situation like this, like this. So if we have a situation like this, where you can see that the datum line is perfectly aligned with one of the circular scale division lines, the reading is actually pretty simple. Here you can see that it is between 30 and 25. So we start from the smaller number and go up towards the bigger number. So 25, 26, 27, 28, 29 is a circular scale division line over here. But in many cases, in other cases, if the line does not perfectly align, for example, if you have a situation like this, that the datum line, I mean, when the ratchet is clicking and you have placed your object in between, and the datum line of the reference line is not perfectly aligning with the with any of the lines of the circular scale division mark, in those cases, uh, we can choose the closest line. That is one way to go for it, but sometimes it can lead to some significant accumulation of error. So another, that's one way to go for it, which is not incorrect. Many teachers and many physics teachers and researchers actually follow that, which is okay. And another method is to go for the same type of measurement. For example, type, what I'm meaning by type is that, let's say you have a situation like this. So can everybody see that the data line over here is not perfectly aligned with any of the line of the circular scale division? Can you see that there is a misalignment over here? Can everybody see that on the video?
Yes.
Okay. So whenever we have that, one other way to go for. Oh, why is my? Oh. So one other standard way to go for is that we choose one type of reading, either the bigger or the smaller, for every upcoming reading, irrespective of the closeness. It means that if we have a perfect alignment, we go for the perfect alignment. We have a perfect alignment 29, we choose 29. But whenever there is a bit of a misalignment, we either choose the bigger one or we choose the smaller one for all the other upcoming readings whenever there is a misalignment. This type of choice actually helps to offset the type of mistake that we might have from the backlash error, which is sometimes developed in a screw-based mechanism over a long period of usage, because the screw threads tend to get worn up and the screw sometimes can become somewhat loose whenever it is moving within the thread, inside threads. So there are two different ways, but for your level, you can pretty much always expect questions. This is usually show up in the MCQ questions, and also for your lab practice, it's also pretty important. So for your purposes, you can always, if it ever comes in your paper 1, it never shows up on paper 2. If it ever comes on paper 1, you can always expect that the examiners are going to give you a perfectly aligned line, somewhat like this, of this sort. And if you are trying to take a measurement for your lab practices, what I would personally recommend that for the first case of misalignment, you can choose whatever the line that you want. So you can choose the smaller one, you can choose the bigger one, doesn't matter. But for all the upcoming readings, if there is a misalignment, choose the same type of reading. Either choose the bigger one as before or choose the smaller one as before. That actually helps to correct some systematic errors. And that's one way to do the list. So this is how we read the circular scale, and then we have the least count. Least count is basically the smallest measurement that a system micrometer screw gauge can read off. For the way least count is measured by pretty much the same formula that we have earlier seen for the Vernier caliper. This is the smallest length and right division, smallest division on main scale. Number of divisions. So what this is, okay, one thing that is important for over here is that this linear scale is basically what represents the main scale. This main scale is actually pretty interesting. You can see over here on top of, above the line, we have 0, and then if you count 1, 2, 3, 4, 5, after 5 you have 5 mark, then 6, 7, 8, 9, 10, you have 10 marks. So in this case, each of these divisions, each of this length represents 1 millimeter. However, under the datum line, we have some lines exactly at the middle of all of these lines. So these lines actually represents the 0.5 millimeter increment, which means that this is 0, 0.5, 1, 1.5, 2, 2.5, 3, 3.5. Intentionally, the half millimeter marks are placed on the opposite side of the 1 millimeter marks so that observing the scale can become somewhat easier to eye. So because if they put all of these lines on the same side, I mean, deciding is it a 1 millimeter mark or a half millimeter mark could prove to be somewhat difficult, because 1 millimeter is not that much of a big space to actually to be divided in two equal pieces to be easily visible by people of all age. So or all type of eyesight. So that's why they place the half millimeter mark at the bottom for better observation. So whenever we're going to place some object over here, this is going to be our main scale reading. The very last line that you can see on the border of the thimble scale or the circular scale is going to be our main scale reading. For example, if you have a look over here, this is the thimble scale, or this is the thimble scale. For example, if you look at this figure over here, open image new tab. It's a pretty big image. So if you have a look over here, that how much is the reading over here? Let's have a look. So this is 0. So we have, if we go all the way over 5, and after 5 we can see the 5.5 line, but we cannot see the 6th line, which means the main scale reading is 5.5 millimeters. And then we have to look out for the best alignment of the. Do you hear some kind of chorus through the mic?
Yes, sir.
আমাদের এখানে কোন এক ধরনের নির্বাচনের প্রচারণা চলতেছে। I have no clue what kind of thing. It comes up every day at the evening.
Selection হয়তো আসছে কাছে, তাই না?
আচ্ছা, I almost said something that I shouldn't have said on a public channel, maybe, because we live in a secular country. But okay. Anyway, I hope it goes away. But if I cannot overpower that sound, and if you have difficulty hearing me through that noise, I'm actually closing my window so that the sound is less. I hope that helps. But if you have difficulty, let me know. I'll try to scream through my microphone, or increase the decibel level gain of my microphone from the software settings. Anyway, so if you have a look over here, that 5.5 millimeter is the main scale reading, and these division number actually give us the circular scale division. You have to understand that circular scale division is just a number. That is not a length. It only becomes a length once we multiply that measurement, that observation, by the least count. Least count happens to be a certain length. For example, you can see over here, smallest division on main scale. For micrometer screw gauge, that smallest division on the main scale happens to be 0.5 millimeter, because you have marks for 1 millimeter. We have also marked for half millimeter. So that is 0.5 millimeter is the main scale smallest division. And number of division on the main scale was 50. So if we do the division, we get 0.01 millimeter, which happens to be the least count of a micrometer screw gauge. It is important that you get acquainted with the terminologies that we're going through. Circular scale division is also sometimes called a thimble scale reading, but you have to understand what is what. For example, the smallest length that we can measure by Vernier calipers, going back, the smallest length that we can measure by a Vernier calipers is called a Vernier constant. That's the designated name. Whereas the smallest length that we can measure out of a micrometer screw gauge, using a micrometer screw gauge, is called least count. So LC doesn't mean least constant or anything else, and VC doesn't mean Vernier count. It means Vernier constant. LC means least count. These are exclusive terminologies for these apparatus, as it has been practiced over the years or whatever. So try to get acquainted with the terminologies so that it can help you. So one thing, so this is the least count of this device. It means this is the smallest fraction of length that it can measure, which essentially means that any measurement that you take out of a micrometer screw gauge should be a full multiple of this. Full multiple of this means what? If you take a measurement out of a micrometer screw gauge, you can have 0.02 millimeter. You can get 1.63 millimeter. You can get 7.63 centimeter as well. Now you might wonder, that's not right. You're correct, that's not right, because if I'm trying to write it into centimeter, I should definitely give another 0. Do you understand why should I give the 0? A length can be 76.30 millimeter. It's possible. 76.30 millimeter is it possible to measurement out of a micrometer screw gauge, because this is falling onto exactly onto the 30th mark. Perfectly all right. But if you are converting this into centimeter value, and if you skip this 0 at the end, you lose the information of accuracy. Providing this extra 0 actually means that whenever this length was measured, it was measured up to this much decimal place. So if I write a certain length that looks like this, let's say I'm going to write 7.63 centimeter, and if I write the length 7.630 centimeter, there is a world of difference between these two expressions. Mathematically, there isn't. They both represent pretty much the same number for decimal scenario, but for physical measurement mechanism, this value represents that this was measured for a smallest length of 0.1 centimeter, or whereas this one, sorry, 0.01 centimeter, this is the smallest fraction value, and this one was measured by an instrument with the smallest fraction measurable of 0.001 centimeter. So this reading was actually made by a much more precise instrument. That's what that extra 0 can mean. But by no means a micrometer screw gauge could possibly give you more than 0.01 millimeter fraction. So what I mean is that you can never have a certain length measurement out of a micrometer screw gauge that could possibly look like this, a 7.6312 millimeter. That is not possible to happen for a micrometer screw gauge, because the smallest length you can measure is up to this much digit. You cannot measure this one. So assuming if you get this number, it means that you are definitely messing up somewhere. You are creating extra precision from your brain or something, or someone, whoever it is doing. So be careful not to do that mistake. So as the least count part, and that basically covers up for the measurement. So if I just go over here for another of these animations that we have a question. This is main scale reading. This is circular scale division, and this is least count. You can find all of these expressions in your book, in all explained in words. But yeah, there you go. Circular scale division, and LC stands for least count. So if I turn up to this animation, which was actually a good animation, I'd say, which has an object over here, and we also have the option to introduce zero error so that I can show you zero error. For example, let's say over here we have no zero error, and we have a somewhat of an object that I can change the length of the object by just dragging up by the mouse, just to make it longer or smaller, it doesn't matter. And then we can try to measure this micrometer screw gauge by simply holding this thing, and by whenever I'm closing this thing properly, have a look. What happened? Micrometer is paused. Try to select the answer or key in directly rather than filters.
Incorrect. Your input is out by 5.91.
Oh, I can actually try to give the answer over, but they're showing the answer over here. How can I make this answer go away? Anyway, I don't know how I can make the answer go away. So let me just show you how this works. So we close in over here. For example, for this length of the object, you can see that we can see the main scale reading over here, which is labeled over here by red. This is a 5 millimeter mark. We cannot see the 5.5 millimeter mark. And if you look up over here, we simply have a perfect alignment for the 14th division. So 5.0 into 14 into 0.01, that gives you 0.14. This much is your primary measurement. And then we have to handle the zero error as well. Now, zero error is a pretty interesting thing. Zero error, before I get into the zero error, এই পার্টটুকু বুঝা গেছে কিনা যে মানে কোর রিডিংটা কিভাবে নিব, অবজারভেশনের ভ্যারিয়েবল গুলো কি কি? প্রমাণ। Yes. I hope that makes sense. For the next part is how do you handle the zero error. It's very important that whenever we use micrometer screw gauge, before we even start to attach the object with the micrometer screw gauge, if you are intending to use the micrometer screw gauge for whatever purpose, I mean length measurement, that's the only purpose. The first and very first thing is that you check for zero error. What is zero error? Zero error is the error that happens for the misalignment of zero. Let me show you what this means. Let's say I'm gonna make the object go away. So if it so happens that there is nothing in between the object, so I have actually made the object go away. So I have closed the object all the way. So if I want, I can make the object come show up once again. No big deal. So the object can be placed over here. Okay. So the object can be moved over here. Oh, beautiful, nice. So let's say the object is not placed over here. Ideally, whenever we're going to close the micrometer screw gauge by means of the ratchet, and when there is nothing in between the two jaws, this is the fixed jaw, this is the movable jaw. By closing the ratchet, we should definitely have perfectly zero length shown on the device because there is nothing in between. So the measured length should be zero, which means we should see half of that zero line over here. Why half of that? Because you should see that there is the zero. So if you are having the zero perfectly aligned, so this circular scale zero should be perfectly aligned with the datum line representing the circular scale reading is zero, and main scale reading should also be zero. So the reading over here, if you observe this whole thing, is 0 plus 0 into 0.01. So altogether the total length is 0 when there is nothing in between. This is what is the ideal condition. This is what is supposed to happen for a perfect micrometer screw gauge. But in many cases, I should say in most cases, this is not what happens. Almost all micrometer screw gauge comes with some zero error. This is because of the manufacturing, and I mean these devices can develop zero errors over time, and to create a micrometer screw gauge that doesn't have any zero error whatsoever can require extremely high amount of precision, which is not worth the price of a micrometer screw gauge because it is very easy to calculate it out. We can also obliterate or take care of zero error by using a screw that usually exists on this side of the micrometer screw gauge. I don't have a physical micrometer screw gauge at my hand in Chittagong right now, so I cannot show this to you. But let me see if I can find an image that actually shows that micrometer screw gauge head screw side, seen from the side. See that screw? This better have that. Not quite. Anyway, just take my word for the time being, because I cannot find an image where I can actually show you that screw very clearly. Usually on this fixed end, there is typically a screw which can be tightened or loosened by a very special mechanism, which you are not going to have access to. So at least not in your lab exam, obviously. If you ask your school instructor, or whenever we're going to have lab, if you ask me, I might show you that how that can be done. But you should never try to fix it with that. I mean, you are expected to observe the instrument, measure the zero error, provided there is any. In almost all cases, you will have zero error, and then you have to learn how to deal with it. That's pretty much what you are gonna learn. So over here, what we have for the micrometer, this is animation, this one is animation, this one is animation. Yes. So in this micrometer animation model, so what we have is that we can. So this is supposed to be the ideal condition, but sometimes this cannot happen. For example, over here, let's say I'm going to introduce some zero by, let's say I'm going to introduce some positive zero. So introducing some positive zero means what? It means that whenever I'm closing the micrometer screw gauge all the way, so I'm actually dragging it by moving it left or right, and it automatically brings to play and pause for reasons unknown to me. But have a look. Ideally, whenever I should completely close the micrometer screw gauge, it should perfectly become zero. But whenever I have chosen a certain zero value, I can actually make it go away. So it is not visible. So there is a somewhat unknown zero over here. So if I just close it over here, you should see that we do not have the zero circular scale division perfectly aligned over here. This misalignment tells us that there is a zero. So So this is what zero error is. Sometimes the zero mark can be below the datum line, sometimes the zero mark can be above the datum line. Now, which position of the zero line should give us a positive error, which position of the zero line should give us a negative error? You can memorize this if you want, but I highly appreciate that if you don't try to memorize, because sometimes students always forget. I used to always forget. Then I try to learn it by logic. Here's the logic. Try to have a look over here. How does a Micrometer screw gauge work? Try to see. Let me come with the other animation. Have a look. This is your zero mark, right? Take a good look. Whenever I'm rotating this thing by pushing it upwards, this Micrometer screw gauge is actually slowly becoming closer. Have a look. Whenever this zero is going up, this gap is reducing. Can everybody see that? Whenever zero is going up, the gap is becoming smaller, which means if the zero is below the reference line, visibly the zero mark of the circular scale is below the reference line. This essentially means that for the error to be not there, I mean for a perfect measurement, this should rotate a bit more upwards, which means this could not go upwards. This zero mark could not go upwards, or this side of the Micrometer screw gauge, this end, movable jaw, could not move as much on the left side as it should have. So how much could it not move? The amount of length that it could not move happens to be the amount of zero error. So what's going to happen? What's going to be the computation that we're going to have if we take measurements without this zero error? I mean, without taking care of this zero error. Ideally, this jaw should pass. How many divisions do we see over here? How many divisions? We can see 8 divisions of zero error. So for a perfect instrument, this zero line should have gone 8 division above. So the length that we have over here is actually showing us an actual positive length of 0.08, which means that when the length of the Micrometer screw gauge is supposed to be perfectly 0.00 millimeter, we are actually getting a length of 0.08 millimeter. Do you understand where does the 0.08 comes from? It is actually coming from 8 into 0.01. 8 is the circular scale division, that is not the length. Once you multiply it with the least count, that is the least count, 0.01 millimeter, that thing becomes a length. So that is the amount of error that we have, which means in place of 0.00 millimeter, we are having this, which basically means no matter what reading that you get, let's say if you get something to be X centimeter long, if an object is actually X centimeter long, you're going to have that object's reading to be X plus 0.08 centimeter long. Sorry, I shouldn't have it right. Centimeter, my bad. So this is supposed to be millimeter. So if an object is actually X millimeter long with a 0.08 error, the reading of the device should be this much, which means we have a bit over measured our length. So the length that we have measured is not correct. It is excess by 0.08 millimeter. That's why we have to subtract this much. And this is why we say that the error can be plus or minus, and error should always be subtracted. So because this error actually physically needs to be subtracted, we define this type of error to be positive error. Or in other words, I can say, whenever the zero mark of the Vernier scale, of the circular scale, is below the datum line, or in other words, I can say, it still could go 8 division for the perfect measurement. It still could, I mean, it couldn't reach to the point where it should have. Then you can say it should be a positive error, because that amount of length should always be added to the measurements, which is going to be wrong. So this represents a positive error, and vice versa, the opposite thing should be a negative error. So in which case, if this zero mark, whenever the both jaws are closed, is above, we're going to have negative error. Negative error, on the other hand, is going to be pretty interesting, because if we have some object to be negative error, you can see that error is always separated. This minus sign is always a true minus sign. We're not going to change this minus sign. Error will always be subtracted from the whole reading. So this is the whole reading, and error itself can be plus or minus. For example, this error was plus error. if we have a minus error, then we're gonna have some minus and some number over here. So practically the negative error is actually ultimately gonna get added to the object, which I'm gonna show you right now. But before I get into that idea, did you understand that why did this thing actually measure 0.08 millimeter more than what it should have? Did you get this part, that the zero line could not reach up to additional 8 divisions up where it should have been? Does this idea make sense?
Yes, sir.
Okay. So let me just set up another negative error. Maybe let's say I'm gonna go for 12 division negative error. So what I'm meaning is that, okay, let's close this. So if we have a zero over here, that is negative error. So let's say I'm gonna close this object all the way. And what you can see over here, that the zero mark is not even visible. Whenever I have closed this thing altogether, you can't even see the zero mark. Where did it go? What do you think? Now, here is a catch. This is what I need you to understand. Have a look at the orientation of the Vernier of the Microscope gauge line. You started by 0, then above 0 you have, this is moving on its own. So you have the 0, and then you have the 5, 10, 15, 20. These are on the above. And right after 45, you get 0 again, which is basically 50 and 0, the same thing. And one thing that I should also show you, that let me just do one thing. Okay. I would like to show you one more thing. That is, whenever we rotate the micrometer screw gauge circular scale or this spindle by one full rotation, this side, I mean this edge, is going to move towards left by exactly half millimeter. This is something that we call pitch. Pitch means how much it moves horizontally or axially whenever it makes one full rotation. So if I make this thing go rotate one full cycle, have a look. I'm starting to go 0. Now you can see that as I'm rotating this gap is slowly becoming less. And when the 0 is gonna once again start to show up over here, the entire thimble scale has moved by exactly half millimeter to the left. I can do this again. Have a look. 0, 5. So I'm gonna start to move it upwards because I'm closing line now. So I'm gonna bring the 0 once again from the other side, and you should see that from 10.5 millimeter, this is gonna be represented at exactly 10. Getting smaller, 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 smaller. And once again, whenever I reach perfectly at 0, we have exactly half millimeter. So this is something called pitch. Pitch is not for some reason, pitch is not very well discussed in your syllabus. I don't know why, but it's just not discussed in your syllabus. Whatever. Key the synonym, also micrometer model. So whenever we have negative 0, if you close the object all the way in, and if let's say if you cannot see the 0 mark, so where did the 0 mark go? You have to observe this thing properly, and you have to decide where did the 0 mark go. You can see that this is 30, 35, 40, 45. So essentially the 0 mark is supposed to be right above the 45 mark. The reason you cannot see it over here, because this is a graphics model and it's not the actual thing. So if it was an actual thing, maybe by turning it a little bit, you would be able to see the 0 mark right up over here, or maybe you'd see a little bit of fractional view of the 0 mark over here. But for this software-based environment, we're not seeing it at all. But just by observing these numbers, you should be able to judge that where the 0 mark is. For this observation, I can see that the 0 mark is above the datum line, because now we have the base thing. Now here is the catch. Whenever you're reading the 0 error, you definitely should not consider the actual reading on the circular scale. You can see over here that what is the actual division line that is aligned over here? That is 38. Do you see that? See, 35, 6, 7, 8. So 38 number division happens to be in perfect alignment with our datum line or reference line. But is the 0 error is of 38 division? What I need you to understand that the perfect scenario would have been if, come on, work with me. Perfect situation would have been okay. This actually helps better. The perfect situation would have been if this 0 was right over here. What is happening right now, because of the 0 error, this 0 has gone up. Try to understand. by how many divisions did the zero mark go up? This would have been the perfect situation if there was no gap and this was the one close. This was this if this happened, this would be the perfect situation, which you don't have. So the zero mark has deviated from its perfect position in the top position by how many divisions? Have a look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the zero mark is 12 division deviated. So the zero error would not be 38. 38 is the value seen on the scale. But by how many divisions did the zero mark actually deviate from where it's supposed to be? That happens to be 12 division. 12 division in which direction? Above, upwards. So what it means that this scale would have been perfect. Hold up. This scale would have been perfect if this was the case and there was no gap. Now the scale needed to be rotated more, which means this jaw had to move more to the left and actually produce a bit of a negative length, because now this device has gone past where it's supposed to go. So what do I mean by has gone past? What I mean is that, let's say this is the actual zero position. The scale, if it was perfectly here and we had zero on the circular scale perfectly observed over here, this would have been the best scenario or the perfect microscope watch. Now when the zero mark has gone up, it means this jaw has moved a little bit on the left side of the microscope watch. This actually means that every single time the device is going to read a measurement, it's going to read this much less, because the jaw is misplaced for the error that is coming along with the instrument. So we just have to add this much missing length to the measurement. And how do we add that measurement? By making the error itself negative, because by definition, because the scientists decided so, error should always be deducted, subtracted from the reading. That's why this type of error is defined as a negative error, so that ultimately negative makes it all positive. Does the logic make sense? That why is it considered negative? Because we are missing out a bit of a length, because the movable jaw has moved farther on the left where it's supposed to be, and that's why we have a bit of a over carried length, and that will be always missing from the measurement, and that's why we need to add it up. That's where the error becomes negative error, which ultimately gives us a positive addition to the reading. বুঝা গেছে কিনা? I hope so. If you have any question, please ask. Let's just take a measurement of this object and then we'll move on to the next thing. So in this,
So what is what if it's the zero error extra? It on the division it shows 25, then there'd be a positive error or a negative error.
okay, the maximum error that they have accumulated over in this device is actually 15. Okay, let me draw this for you. I'm going to try. For everyone's understanding, what Ryan just asked me is that what I have been telling you is that how to decide that where the zero mark is by observing these numbers. So if these numbers are smaller than 25, you have to believe that the zero is below the datum line. If these numbers are above 25, they are supposed to be above the datum, because these are on the closer side of the other one. Ryan just asked me, it's a pretty interesting question, that what if this line is perfectly 25? What do we do then? That's your question, right? Being perfectly 25. If it's perfectly 25, then how do we handle that? Try to understand. There is a very simple solution for this. This is your microscope watch. This is your circular scale, and here comes the shaft. Let's say you have the zero mark over here. The first thing that you need to understand, when the two jaws will be perfectly closed somewhere within this device. So here comes the jaw and here's other jaw. when the two jaws will be perfectly closed, this end of the circular scale should be somewhere onto this zero mark. This is the first thing that you need to appreciate. Then, let's say you are now trying to find out the zero error, and there is a ratchet, and it's slowly starting to clockwise movement right by your right hand, the ratchet. And this thing is slowly closing onto zero. What you need to see is that does this edge go past the zero mark and then gives you 25, or is it in front of 25, in front of zero? The zero line, zero mark might be cut, might not be cut, but what you need to judge is that is the edge of the circular scale thimble has gone over whenever look vertically. Do you please understand what is parallax error?
So it's when there is a mistake in reading with your eye.
Due to what?
So angle.
Due to an angle, exactly. I'm going to just explain the idea of parallax error a little bit so that I can actually go on with it, because this is a pretty important factor that it is really properly understand what a parallax error is. Let me just show you. So have a look. The idea of a parallax error is that because of your eye position not being in the perfect place, if you read different values, that's what it meant by a parallax error. For example, there is a beautiful figure for this thing. Have a look. Let's say you're trying to measure the length of an object. This is okay. Yes, this is actually a very beautiful image. Do we have any bigger version of this? 20 by 560. Okay, this will work. Let me explain what parallax error is. Parallax error is whenever we have a little bit of error in reading because of the position of eye. Have a look. Let's say this is a ruler, and we are trying to measure the length of this red line. And for some reason, there is a bit of a gap in between the two. For example, let's say this is a piece of glass. The glass has some thickness. Underneath that glass, there is a line, and you are placing your ruler on top of the glass to have a measurement of this line. So you have attached this left side on somewhere on the starting point. Let's say that was done correctly. Now you want to observe that how long it is. Have a look. Because of the difference of eye position, the length of this line can appear different. Have a look. If you're looking vertically from above, you are going to measure 4.8 centimeter. If you're looking at some angle, this is 4.6 centimeter, because have a look, this teal color line is coming across and it is measuring at exactly at this point. Can you see that, everybody? This is the intersection point of the vision. Can you see that? And this is the intersection point for this point. So if you are having that problem, that's when, so not because if the observation is not done perfectly vertically or easily from on top, we're gonna have a bit of an error because of the angle developed over here. But that is not the case if this gap did not exist. If this gap didn't exist, then measuring from anywhere will still get 4.8 centimeter. So that's what this image tells us, that parallax error vanishes if there is negligible thickness of the ruler or if the scale is placed vertically on the surface. Now, here is the thing that I would like all of you to consider. Take out any of your 6 centimeter ruler, 6-inch ruler, the 50 centimeter ruler that you have that comes with your geometry box. And if you have a good look, you'll see that the print of those ruler are done on the lower side, on the flat side, not on the top side. Take a look. I'm talking about plastic ruler, not the steel ones, the transparent rulers. Do all of you see that? The printing of those writings are on the bottom or the flat surface of the ruler. They are done in that way so that we can have so that we are not troubled with parallax error. So that if you place it onto your piece of paper, every single time you can measure the same length, because the page line and then that printout of the ruler, they will be really close to each other. If they made this printout on top of the ruler, then there will be significant gap because of the thickness of the ruler. That can lead to parallax error. This is what we mean by parallax error. It's a very nice figure and nice one. Now, the reason I went to the idea of parallax error is to make sense that whenever we are going to read the micrometer screw gauge, it's very important that we look vertically down. We should not move our head to the left just to see that, can we see that last line right underneath that circular scale, the thimble line, thimble border. No, you shouldn't do that. Just look vertically down and judge whether you can see which is the last line of the main scale that you see. If it's a top line, it's a full millimeter mark. If it's a lower line, bottom line, it's a half fraction millimeter mark. So that's how we do the observation to begin with. And then what is important? Now, as you rotate, so coming back to the question of Ryan, that what if this number is 25? As you rotate this thing now, rotate this scale, you should see, does this border, does this thimble scale border goes past the 0 mark, or does it stop before the 0 mark? Ryan, are you getting my point?
Yes, sir.
If it is going past the 0 mark, that would actually mean that there is a negative error. Because this actually means what? That this thing has moved more than where it should have been. So if it moves on the left side, you basically coming up on the negative side of a number line. If you consider this is your 0, this is your number line. So actually, I shouldn't get to an idea of number line. But if the thimble scale moves past the 0 mark, then this 25 would be a negative error, because that would mean that your thimble scale or the circular scale has moved more than where it should have been, which means every single time you're going to measure something, you're going to have that much length less of your measurement, so you should add it up. And if you see that the thimble scale actually does not go past the 0 mark, you can still see the 0 mark, and you have the alignment at 25, then definitely it is a positive error mark. The idea of positive error or negative error is all lies that did the circular scale go past where it's supposed to be, or did it stop before where it's supposed to be? That's the judgmental point. Do I make sense?
Yes, sir.
বুঝা গেছে clearly?
Yes, sir. So, sir, অন্য রিডিং এর জন্য কি স্যার একই ভাবে করতে পারি, লাইক যদি লেফটে থাকে দেন নেগেটিভ এন্ড রাইটে থাকে পজিটিভ?
Not quite. I would say not quite, because of one specific thing. If you are having an alignment at 25, it means it is really off for the central line. I mean, either if it is at 25, I mean, if you are actually getting the reading 25 over here while measuring for 0 error, I'm not saying it's impossible, very much possible, it can happen, maybe not so common, but yes, it can happen. In that case, the line of the 0 mark would have some significant information to give you. But one of the other things that I need to appreciate is that these lines that we draw on a micrometer screw gauge, for example, these lines that we draw on the micrometer screw gauge, these lines also have some thickness, right? Try to appreciate this. These lines have some thickness. So as we are rotating this thing, can we see that micrometer screw gauge clearly or not? That can be a question of good judgment as well. You shouldn't try too hard to see that line. You should try to just judge, can we see that line, yes or no? If you can see the line, you have that reading. If you can't see the line, then the earlier line, which is pretty far away, I mean, at least less than a half millimeter away, that is your reading. So the reason I'm bringing about the idea of thickness of line, because you just asked me that, can we use this idea that whether the jaw moved beyond 0 mark or stopped on the right of the 0 mark, can we use that idea for all other cases? For all other cases, the judgment of 0 mark being above or below would always suffice your requirement, because it is possible for certain screw gauges that you can also have your 0 mark above, but it has not, but the line is still very much visible. For example, if you have 0 error of, let's say, maybe -5 or -6, you'd still be able to see that line. You'd still be able to see that line. But that is a definite -6 error, -6 division, circle scale division, or minus 0.06 millimeter of error. So if you have a contradicting case of such a big number for circular scale division like 25 or something like that, then the judgment of overlapping or not reaching the zero line can be used. I mean, this is a very special case. But for other cases, for numbers close to 0 or close to 50, you should preferably use the idea of whether it's above or below, because in most cases you would be able to see that line, because the line that we have printed has some thickness. Ideal case, it shouldn't have thickness because lines are supposed to be one-dimensional thing. I mean, you move a point, you get a line, but lines that are inscribed on our instrument do have thickness. Could I make my point across?
Yes, sir.
মানে বুঝছো, মানে আমি কেন লাইনের থিকনেস এতক্ষণ কাকা করলাম এটা কি বুঝছো?
জি স্যার, বুঝেছি।
Any further question, anyone? আইমান আবতাহি, তুমি কি আমাদের এটু আবতাহির ভাই?
Sir, what?
Do you have a bigger brother?
Yes.
Goes to mastermind?
No. Sir, my bigger brother is Armand Labib.
ওহো, তুমি হচ্ছে আমাদের করাবো। Okay, the next thing that we can pick up is idea for moment. আচ্ছা, আমি অ্যাকচুয়ালি রিডিং দেখানো ফুল প্রসেসটা শেষ করে নাই, so I was actually moving on from zero. So if we just have an object over here of unknown length, whatever, first thing we do is that we measure the zero. For example, for this device, we get the zero error to be perfectly how much? Stop at zero. So this device has a zero error of minus 0.12 millimeter. And then if you're trying to measure the length of this whole object, let's say we open this up, bring the object in, close this thing all the way. So it can now move to the right, but it cannot move to the left any further. This is the last version that we have. So if you have a look over here, actually the reading is pretty well shown over here, but you can also look at it from this position as well. You can see 0, 1, 2, 3, 4. You can see 4.5. You can see the lower marks. 4.5 millimeter is the main scale reading, and then the circular scale reading is 15. So 15 to 0.01 gives you 0.15 millimeter, and that much is your main scale reading minus the error, which was minus 0.12 millimeter, gives 0.12 millimeter. So altogether, the object happens to be, the distance happens to measure as 4.77 millimeter. That's pretty much how it's done. One other thing that is pretty important whenever we're using microscope or Vernier Callipers or any other measurement device that we use, you can use multimeter for measuring current, voltage, or resistance, or whatever. One thing that is always true is that to get a reliable reading, we should always take measurements multiple times, at least 3 times, and do the average. And measuring an object 3 times doesn't mean that we measure the same object in the same place 3 times. For example, if we have a piece of wire, let's say we have a piece of wire. Wire is basically a cylindrical object. So you have a piece of wire. You're trying to measure the diameter of the wire. It is recommended that you use your microscope gauge in approximately 3 different places. Ideally, it is expected to have uniform diameter, but it might not have uniform diameter, in which case measuring the diameter in different places actually can help. So we measure it in different places, If you come up with exactly same numbers, well and good, no problem. Hats off to the manufacturers who actually made a really uniform wire. But if you get somewhat different reading, it's also perfectly okay. That can very well happen. So in that case, you have to average it out for the microscope reading. One thing that you need to understand that there is a difference between measured value and calculated value. This is really, really important. Any measured value is what sometimes what we call a raw number, which you get directly out of an instrument, and any calculated number is basically what we get out of the mathematical calculation. For example, if I give you a bit of an idea, uh, let's say you have a cylindrical object, and I ask you to measure its volume. There are two different ways you can go for it. You can measure the diameter, which is a measurement, and you can measure the height, which is another measurement. You can use 1/4 pi b square h as the formula for volume. So in this case, diameter would be a measured value, height will be a measured value, whereas the volume would be a calculated value. That's one way to go for it. The other way you can go for it is have this object and measuring cylinder, which was earlier partially filled with some liquid, and submerge this whole object all the way down and measure how much height volume height rise happens to the liquid body to measure the volume of the object directly out of the measuring cylinder. That's also possible. So in that case, we are directly measuring the volume by a mechanism that is available for it to measure the volume. So the reason I'm telling you this is that calculated values can have some effect of significant figure. Typically, we go for a 2 significant figure value for your syllabus, or a 3, up to 3 significant figure is also allowed, but we do not go for more than 3 significant figure. Whereas raw values or measured numbers should always measured numbers should always be mentioned or recorded up to the appropriate number of decimal place of that device's measurement capability. For example, if you're using a micrometer screw gauge, the smallest fraction is 0.01 millimeter. Whether I express your measurement in centimeter, whether you express your measurement in meter, doesn't matter. As long as you're mentioning a raw value, you should keep this decimal place up to the record of the number. But whenever you do the average, then you can very easily round it up to 3SF or 2SF as per your convenience. So that's another thing that is pretty important. So,